So having looked at the hydrogen emission spectrum in the previous video, in this video we're going to talk about the first model of the atom that was developed by Niels Bohr, and specifically for hydrogen, that was able to explain what's going on here. One of the key things to realize here is that the light that's coming out is corresponding to the energy of something inside of the hydrogen atoms. And so we can either see energy going into the atoms or out of the atoms, and that can show up as light. And this correspondence between light and energy is one of the ways that we're able to get all this information about quantum mechanics. So when we see this emission spectrum, right, so when we have a bunch of hydrogen atoms and we pump a bunch of energy in through electricity, when they lose that energy comes out as light. And that's what we're observing when we observe the emission spectrum. And we're able to see that light doesn't show up at every different possible wavelength we could see. It shows up at very specific ones. And so that shows that the energy inside of the hydrogen atoms, yet again, is quantized. So energy comes in distinct chunks. Because if this behaved like a large macroscopic object, like something we could hold, we would expect that you put some energy in, you can get any value of energy out, and the light would come out all sorts of different colors, instead of just these very specific colors that we observe in the emission spectrum of hydrogen. So what's gaining and losing energy inside of an atom? Well, at this point, scientists did know about the fact that we have a nucleus and that we had electrons doing something around the nucleus. They're out here somewhere. And that's our goal for this chapter, is actually to dive into what is happening with the electrons around the nucleus. And so it's actually the electron. It's not that the nucleus is mostly just going to do its thing. It's a lot heavier. The electron is going to be able to gain and lose energy. And so when we observe light interacting with matter, we're usually observing things happening with the electrons. There are exceptions to that. There are other ways that atoms, and especially molecules, can gain and lose energy. For atoms, it's primarily the electrons that are just going to go up and down in energy. And so Bohr's model was, he knew that there was a small positively charged nucleus. By this point, Rutherford had already established that through his gold foil experiment that we talked about way back in chapter 1 or 2, whichever it was. I think it was chapter 2. And so Bohr proposed this model for the atom that we have for hydrogen. We have a single proton. That's the nucleus of a regular hydrogen atom. There could be neutrons here. It doesn't really matter. And our electron is orbiting around the nucleus. I'm just going to remind you right now that this model is not 100% correct. In fact, there's a lot of parts of it that are not really correct at all. But it actually agrees with the experimental data. And that's why it's useful to still talk about it, even though this isn't quite correct. But it has a lot of the fundamental ideas. And Bohr proposed that this electron could orbit the nucleus only at specific distances. And we can label these with a number, n. So we could call this closest one n equals 1, then n equals 2, then n equals 3. We're going to see this this is what is called a quantum number show up later. And we're still going to use the same integer to mean this. And so, again, the electron's not actually doing this. We can't actually say it's orbiting at a specific distance. It's really about probability, and we'll get to that soon. But what's happening is when the electron changes energy, it can only change to specific values. So it can go up to 2, or it can go up to 3, but it can't go partially in between. This was Bohr's idea. And that part is correct. That part of his model is correct, that there are specific energy levels inside the atom, and the electron can only occupy those very specific energy levels. The energy is quantized. And so what we're observing in the emission spectrum is energy is coming in the form of electricity, because we have these hydrogen atoms inside of electrical discharge, and our electron moves up to one of these higher energy levels. Maybe we'll do n equals 3 here. So it's not in n equals 1 anymore. I should just erase it because we've added energy into the system. And the electrons in the electricity hit the hydrogen atoms and pump it up to higher energy levels. The electron can't stay there, though. The nucleus is going to pull on it, and when the electron goes back down, it can go down to 2 or to 1, and all the transitions that go back to n equals 2, so if our electron ends up here, these are the ones we observe in the visible part of the spectrum. These are the ones that Balmer observed originally. And so we get a bunch of different transitions that are specific. So I want to pull in a figure from your textbook that shows this in a little bit with a few more examples. Let me do this and blow this up. So this is a little bit, this is what we call an energy level diagram. This is a little bit of a different way of looking at this, but similar idea. And we're going to see quite a few of these throughout our course. So let's take a little bit of time to understand what we're looking at here. What we're seeing here is these n equals 1, 2, 3. These are these orbits that I was talking about. Again, the electron doesn't actually do this. It doesn't actually orbit around like this. So we talk about orbitals, which we'll get to very shortly. But these represent the energy levels that are available in the hydrogen atom. And our y-axis here is energy. So as we go up, we're getting to higher energies. So there is, in each of the lines here, represents a transition between energy levels. So if we're looking at all of the energy levels that go back down to n equals 1, our lowest possible energy level, these lines show up in the spectrum. They're just not visible lines. We can't see them in the visible part of the spectrum. These all show up in the ultraviolet, as it says here. Because we can see that they have a lot more energy, these arrows are longer, so that means a bigger difference in energy, which means higher energy is equal to higher frequency, which is equal to a shorter wavelength. Ultraviolet photons, ultraviolet light has a very short wavelength. The ones that are in the visible are all the ones that go down to n equals 2, and then the ones that are in the infrared are down to n equals 3, and there are additional series that we could get to n equals 4 and n equals 5 and things like that. There is a point that we call n equals infinity, which is like the maximum possible energy we can get to. Based on Bohr's model, there's some point at which the electron just leaves. So this is electron leaves when we get to n equals infinity, or we could say this is the ionization, meaning the electron leaves, it turns into, and that will turn our H into an H plus an electron. Let me move that just so it's not behind my head. There we go. Okay, so this is the idea of the Bohr model, is that there are distinct energy levels within the atom, within the hydrogen atom. And again, we're seeing this same idea of quantization of energy, much more dramatically in this case, I think, than either the black body radiation or the photoelectric effect, where we see, because of this, the quantization of energy, these distinct spectral lines in the hydrogen spectrum. And the great thing about Bohr's model is that he could take that model and calculate, just based on the model itself, what the differences in energy were. Based on the, we're not going to go through that derivation, but he goes through this calculation, and he proposed that the energy of an energy level is given by negative 2.178 times 10 to the minus 18th joules, so a very small amount of energy, times 1 over the value of n squared. So it's going to change depending on what value of n we're looking at. When we take differences in energy, this is going to matches with the Rydberg formula. And so this was a big step forward, because Rydberg's formula just came from the experimental data. It didn't have any theoretical underpinning. Rydberg said nothing about any electrons or energy or anything. He just said, if we follow this formula, you can predict where the lines in the hydrogen spectrum will be. What Bohr did is said, okay, I can get that exact same formula knowing nothing about the spectrum, just knowing that we have these electrons orbiting around a nucleus. Again, not what they're actually doing. So this was a really great step forward, but we need some way to justify why the electrons would stay in these particular orbits, why energy is quantized. And so in the next video, we'll talk about the idea that electrons, we mostly think of them as particles, but just like how light, which we usually think of as a wave, can behave like a particle in terms of being photons, particles, mass, things that have mass like electrons can also behave like waves, and that'll be our next video.